Right, we'll now just go to Mick Gunter. Thank you, Mick.
You'll have to excuse my slightly croaky voice. I've been to bed at 8 o'clock the last 2 nights to try to get it better, but that hasn't worked. Haha. Okay, transition curves in V10. Nice little quick light entertainment before a break. And I thought the first thing we do was just do the standard little, almost from the last conference, just a quick little refresh. And it is that simple thing. We all know this, but it's just a little readdressing of the thing. A transition curve is a curve between a straight and an arc, or an arc and an arc. So it's just that simple example there of a straight to a transition, or for a lot of the railway guys where it's necessary to join two arcs together for whatever reason there might have been. Okay, transition curves supported in 12D. We have the good old clothoid. It's just used about everywhere by roads, a lot of rail authorities. It's a very good approximation to a spiral. The New South Wales cubic parabola, it is not a spiral. It's the one that's, anyway. And the West Rail cubic spiral. Also, it's an approximation to a spiral, but not a true spiral. Elsewhere in 12D, we also support the natural clothoid, as we call it. That's the one that you see just spins into infinity. It is the only true spiral. There's the cubic spiral, which is an old surveying funny guy. It's in there, but again, it's not a cubic parabola. We have the Bloss curve, which is one that's used in Europe and Germany especially, where they use that in conjunction with the clothoid in the same alignment, depending on the radii and the curves and speeds. And those other two funny old sinusoidal, cosinusoidal, which are in, anyway, we just have them in there. Okay, are they the same? It's always one of these things we just like to reinforce. No, they're not the same. They all can be quite distinctly different. So here we've got a bit of a silly curve just to exaggerate the differences. And the differences. So when we look at them, you can see that there's actually a bit of a natural order progression as they go across as to where these guys lay in space. And one point I'll bring up a little bit later on is you'll notice that this is actually where the tangents occur, and you'll notice that the cubic, New South Wales cubic, is actually quite distinctly different to the other guys as to where it actually runs in space. Okay, what needed to change for V10? Well, for things like components, as Peter alluded to yesterday as he showed in a few of his little things, when we've got components, we're doing filleting, we're offsetting. We needed something to be able to parallel, or no, I can't use the word parallel, it's offset, it is slightly different. So we did need a new curve type, the offset transition. And that's a typical case there. There's a couple of, there's a road, we want to put a little curve returns off on the side, we've got some transitions there. We've got to be able to create something out in space that all the magic of Hahn stuff can work on. And the other big thing was, one thing to make clear, the superalignment in V10 superficially might look like the superalignment in V9, but in fact, it's almost a complete rewrite under the scenes. And so my little piece of things there was when we came to do the transition curves was just to revisit accuracy and speed right through it. So it wasn't a 5-minute exercise. It actually probably took me 3 months or so to do most of this stuff, and it really was Lee being very kind to give me all the time necessary to go to and get this stuff absolutely right. So there's a good old-fashioned superalignment, just curving from right to left. And for V10, we just simply have the offset variety. It all looks so simple on a piece of paper. Okay, so what is an offset transition? It is not the V9 curve, and as I made the point, a curve that's 20 metres offset clothoid is not a clothoid anymore. It's a different sort of beast. And yes, in its simplest form, it is a clothoid. It mirrors it. You have the V9 curve. Yes, and all the transition curves in V10 now have the offset variety of them. This was one of the bits of work to make sure this is fairly simple for us to do. Fairly simple speaking here. And the next one was, are they complicated? Well, I remember the last conference, someone thought this was a bit complicated. They thought that was pretty high tech. So for V10, I made the point, I thought Peter probably thinks that this stuff is complicated. And that's serious. That's the sort of stuff we have to solve to do things exactly. So, are they complicated for you? And the answer is no. It is absolutely simple. If you're doing most of the work, it's all done in the background, or otherwise you can just go into your super alignment editor and stick an offset in. That's all that's necessary. Okay, the other thing to talk about was compatibility. All the V9 types will migrate to V10 with the possible exception of anyone in New South Wales using the cubic parabola. Now, the cubic parabola is extremely sensitive to precision of calculations. If you were to use a very large radius and put a 50-metre transition curve into it, packages will let you do it, but you need to realise there's more decimal places than available in the universe needed to represent it accurately. So there are migration problems. And we've seen this, I know the guys who've dealt with like land XML import into 12D from other packages and wondering why it doesn't work. It's simply that 4 or 5 or 6 decimal places is nowhere near enough in some situations. So this is just one to be aware of. Yeah, that's it. Compatibility. Well, obviously, 12D field can use offset transitions, no problems at all. Half of the speed ups we did in there were for 12D field guys so they could take huge data sets out in the field and process them efficiently. And if you're using something else, then unfortunately it's going to have to be approximated because they don't have it's just not there. And that was it, short and brief. It's just basically, so finally we do have the magical offset transition. It was when I first joined up with Lee finally 5 or 6 years ago, that was one of the things on my hit list, and we've finally ticked that box off for V10. So that's it, short and sweet.
Right, so luckily you guys don't have to solve those equations. I'm a mathematician, I still have troubles in my headspace getting around some of them. But say the whole idea there was to make it all accurate so you can use all those things and not have to worry. And I think we're the only in the package in the world that I know of, certainly, that even talks about offset transitions, let alone having them inside your software. Some of the things for version 10, say underneath the hood, yes, all the calculations for all our works, all the things we did have been totally rewritten. So that went on for about 2 years. So that's why version 10 has had a little interesting birth. But for some of these things like the New South Wales cubic parabola, I think you got about, 100 to 1,000 times speed up in some of that stuff. So it means you can do huge jobs and things like that and still get very quick access to things inside the super alignment. So we were doing stuff in the background, not just having good lunches every day. And a lot of it is to rework a lot of things so we're ready for the future, so we can go even to bigger data sets on smaller machines and things and be very, very accurate and correct, but also give you the speed that you need. So that was one of the projects we're working on to give you the proper offset transitions. With that as well, the super alignment, as we said, that it has been totally rewritten. It's very, very compatible going from V9 up to V10. Say it's mainly the New South Wales cubic parabola where they don't necessarily have the precision. So just beware, if something does happen, just get on to us. Also, with all the different cases in the super alignment, all the different things you can have in there, and there's more cases, if you do have a problem going from 9 to 10, just let us know so that we can get in there and fix it up, because it's not simple. Some of this mathematics is very, very nasty, and there's thousands of different cases. So jump on the forum, talk to your distributor who'll check it out for you, and then they'll get through to us to see and give us the example. If you do have a problem, we need an example. Just to be told, oh, something doesn't work, it's just impossible. So we always need, say, just a small project with the data in it. Even if you write it out, if you don't write out to enough precision, it mightn't help us. You need to write some of these things out to a full 16 decimal places for us to be able to get it. So you're better off just sending us the 12D model project. Which brings up one of those things that Mick mentioned. People reading data from other packages. And land XML is a classic. Things they say, oh, there's extra points in there. Well, the data we got from there does not have enough precision for us to have things tangential. So we have to put extra points in there so you get tangencies, because we just can't go in there and say, why can't we fix it up? Well, what do? Do we change your radius to make it work? Or do we change your tangent points? There's decisions that we wouldn't like to make for you on the fly. But that's the problem when you bring in data through other things without enough decimal places. Things are no longer tangential. because most things of those formats are what we call just elements, as opposed to things where they're computed, where you're told how they build them up so we can do it accurately. The IP method, it was a computational definition. You give your IPs, you say what the radius is, what the spirals are on it, and we calculate the rest from it. So anyone you're using your IP definition, everything's sweet. You start just getting elements from various packages or from AutoCAD or anything else. If you go to a few decimal places, things are no longer tangential. So you have to add in extra points and extra things. So that's why you do get some problems. It's not that we can't do things, but we don't want to change your data. If we then changed your radius on you and moved it by even 10 millimeters, someone will say, oh, and this was accurate to 3 decimal places, it's no longer correct. They're the sorts of problems you've got. So be very careful bringing data around. How many decimal places is very important, and we got caught ourselves. We got our call. One of you would have seen on the forum is when you want to get certain data across using 12D ASCII, we then come back and said write it out to 8 decimal places. Because again, with some of these transitions, we need to do that internally for those things, but we haven't got caught. And when we know a bit about mathematics and things like that, but so it's easy to get these things wrong or not real.